Hi there, the Math Dog here. This is a trigonometry video where I'm going to look at and derive the trig identity sine of a plus b. In other words, the sine of the sum of two angles is equal to the cosine of a times sine of b plus sine of a times cosine b. Now before tackling this video, it would be helpful to be familiar with these properties. Cosine of pi over 2 minus theta equals sine theta, and sine of pi over 2 minus theta equals cosine theta, and the cosine of a minus b equals sine of a times sine of b plus cosine of a times cosine of b. I'm actually going to review all these here. I have other videos with these proofs done. However, I always found it frustrating as a student where a proof just said, here's this, and it's like, just trust this to be true. I didn't find that to be a very good proof, because it's just like, just assume this to be true. Anyway, so this will take a little bit more time here because I'm going to go through these properties as well. Even though I've done them before, I'm just going to have them at your fingertips here so you can see it as we go along. Okay, so a quick review. Cosine is an even function. An even function f of x is such that f of x equals f of negative x. Visually, it is a function reflected across the y-axis and it matches itself. It is even. So if a function, if I take the function reflected over, in this case, if I reflect a function over the y-axis, that's a line of reflection. If I get a mirror image of the function, then it is even. Another way of seeing this is if you reflect the function and you get the same graph, it's even. So again, here's some function. This is a parabola. Say this could be f of x equals x squared. So if I take f of x equals x squared, and then I take f of negative x, in fact, I'm going to get the same graph. So thus we say f of x, if f of x equals f of negative x, then we say f is even. So in the case of cosine, that would mean cosine of x is equal to the cosine of negative x. In fact, this is the graph of cosine right here, and you can see that if you flip this over reflected over the y-axis, it matches itself. Okay. An odd function, f of x, is such that f of x equals negative f of negative x. So visually, if a function is rotated 180 degrees about the origin and it matches itself, it is odd. So you can see here actually that a double reflection, in fact, is a rotation of 80 degrees. That's just another little interesting piece of information here. So if I have a function f of x, let's say this could be like x cubed. If I reflect it over the y-axis, this is going to be f of negative x, and the graph looks like this. Clearly that these graphs do not match each other, f of x and f of negative x. However, then if I take f of negative x and reflect it over the x-axis, that would give me negative f of negative x, which in fact is the same function in this case as f of x. Thus if f of x equals negative f of negative x, we say f is odd. So sine, which is the graph here, this is sine of x. You can see if I rotate sine 180 degrees like a propeller, it will in fact match itself. You can see that right here, and that actually goes true for the whole thing. So again, if you rotate this 180 degrees, it's going to exactly match itself. Thus sine x equals negative sine of negative x, and we will need that in this proof. Okay, then quick review of horizontal translations. So if I have a function f of x and I shift it h units to the right, that's f of x minus h. Okay, you might think, well, that should be x plus h. Well, it's not, and I actually have another proof on horizontal translations, or another video on horizontal translations, where I go into detail to show why this is actually a shift to the right. Then if I have f of x equals f of x minus h, that actually is a slide left, or translation slide, same thing. This will be, this transformation here, or this translation, slides f of x h units to the left, and we will need this information in this proof. Okay, now I'm going to demonstrate how cosine of the difference of two angles, a minus b equals the sine of a times sine of b plus cosine a times cosine of b. So what I've done here is I've constructed two unit circles. So they have a radius 1, they're congruent, and I've constructed two congruent triangles here, or I've sketched two congruent triangles here. So I'm going to call this angle theta here, this is angle theta here. I've marked the corresponding sides that are congruent. So particularly the length of segment AB is going to be congruent to the length of segment MC. So remember on a unit circle that all the coordinates can be described in terms of cosine theta and sine theta instead of just xy. Okay, this is the x-axis, this is the y-axis. So in these triangles, in this one, this is the angle at 0 degrees or 0 radians. This has coordinates 1, 0. I'm going to call this is my angle theta, so this point C has coordinates cosine theta, sine theta. Now for this triangle AOB, I'm going to call this angle B right here, and then this point I'm going to call big B. Actually that should be angle A. Okay, and I'm calling this point B for some big B, it doesn't really matter, but that's going to have coordinates cosine A, sine A. Then this will be angle B here. Okay, and this has coordinates of cosine B. The point A has coordinates cosine B, sine B. Okay, and notice that then theta, this angle here, will be equal to the difference of angle B minus angle A. Okay, so now again I've noted that triangle AOB is congruent to triangle MLC, therefore corresponding parts are congruent. So particularly these two segments are congruent. And again I mentioned that circle OA and circle OC are both unit circles. Well, we know again from the corresponding parts of congruent triangles that segment AB is equal to in length. The length of segment AB is equal to the length of segment CM. Okay, so using the distance formula, now remember distance formula is D equals the square root of the difference of the x coordinates plus the difference in the y coordinates. So that's what I'm going to apply here. So segment AB I can write as the square root of cosine of B minus cosine of A quantity squared plus the sine of B minus sine of A quantity squared that should be sine B the way I'm doing this. Sine B minus sine A quantity squared. That's the length of AB. And that's going to equal the length of CM. I'm going to call that the square root of the cosine of theta minus 1 quantity squared. Plus the sine of theta minus 0 quantity squared, which is just sine theta, quantity squared, which is sine squared theta. Okay, so now we're going to multiply this out. So remember, you actually got 4 multiplications here. Remember that a minus b quantity squared is a squared minus 2ab plus b squared. So you've actually got 4 multiplications. So this is a binomial squared. That's what this is. So this is going to be the square root. And what we're going to do now is we're going to square both sides, get rid of the square root sign. Okay. So here we get, cosine squared b, because cosine of b quantity squared is cosine squared b, minus 2 cosine B cosine A, as we double this product, plus cosine A quantity squared, which is cosine squared A, plus then we have this. This is going to be sine of B quantity squared, which is sine squared B, plus, minus 2 sine B cosine of A. No, that's sine A, sorry. And then that's going to be plus sine squared, sine of A quantity squared, which is sine squared A. And then this will equal, this is going to be cosine squared theta minus 2 cosine theta plus 1. All right, so now there's actually another property that we need here that I should have mentioned. And this is one of the most important trig identities. This is one of the Pythagorean identities. So again on the unit circle, this would be 1. We'll call this x, this is y, the radius is 1. Okay, so this is angle theta. Again, so notice that by the Pythagorean theorem, x squared plus y squared equals 1 squared, which is 1. But from basic trig of SOHCAHTOA, cosine is adjacent hypotenuse, so the cosine is, again, adjacent over hypotenuse. Well, this is the opposite. That's the hypotenuse. That's got to be adjacent. So cosine of theta equals x over 1. Cross multiplying, you get x equals cosine theta. For sine is opposite over hypotenuse, so you have sine theta equals y over 1. Using cross multiplication, you get y equals sine theta. Therefore, making substitutions here, x squared is going to be cosine squared theta, and then y squared is going to be sine squared theta, and that equals 1. And we're going to use that right now, because notice here I have on the left side, right here I have sine squared A, and I have cosine squared A. Well, the sum of those has to be 1, so I have 1 there, plus, then I have cosine squared B and sine squared B. Well, that's this trig identity right here, so that's going to be 1. So then I have that, now I have minus 2 cosine B cosine A minus 2 sine B sine A. That's the left side, and then that's going to equal, okay, so here we have cosine squared theta minus 2 cosine theta plus 1. Okay, so I'm going, oh, I missed something here. So on this side here, when I multiplied this out, I had cosine squared theta minus 2 cosine theta plus 1. That's great, but I forgot to put in the plus sine squared theta. Did you notice that? So, my fault. So now we have this. So that's going to make this on the right side here. Notice this and this is just 1. Then I have a plus 1 here, minus 2 cosine theta. Okay, so now notice that I have 2 over here, 2 over here. They will cancel out. So I'm now left with negative 2 cosine B cosine A minus 2 sine B sine A, and that equals negative 2 cosine theta. Well, now I can divide everything by negative 2, is what I do to one side, I have to do the other side. So now I have cosine, and I'm going to reverse the order here, cosine A cosine B plus sine A sine B equals cosine theta. But remember, we defined cos theta up here to be B minus A. Okay, so we have cosine A cosine B plus sine A sine B equals cosine of B minus A. All right. So remember that we have the property of cosine theta is cosine of negative theta because cosine is even. Therefore, the cosine of B minus A equals the cosine of the negative of B minus A. So that equals cosine of double negative here makes A minus B. So our final conclusion using this and this, I can say the cosine of A minus B. So up here I have now graphs of sine x in red, blue is cosine x, green is negative sine x, and yellow is negative cosine x. So remember, if you go from f of x to negative f of x, that's a reflection over the y-axis. That's why sine here is red and green is negative sine, because notice we flipped the sine function over the x-axis. And the same thing for cosine. Cosine x is blue, yellow is negative cosine x. Now let's do a quick sketch of the unit circle. And I'm not going to completely repeat myself here, but the coordinates here are 1, 0, 0, 1, negative 1, 0, 0, negative 1. And remember that any point on the unit circle, this is the x-axis, this is the y-axis. Remember, we drew a right triangle here. This is radius 1. There's your right angle. This turns out this is x, but that's also sine x. I'm sorry, cosine x. We did that on the previous couple minutes ago. We talked about this when we derived cosine squared theta plus sine squared theta equals 1. So x equals sine cosine theta. Y equals sine theta. Therefore, any point on the unit circle which has coordinates x, y is also equal to cosine theta, sine theta. So we could do a quick sketch here of what sine and cosine looks like, and I find this to be a useful sketch to answer some of these trig identity questions. Okay, so we'll draw a quick sketch of sine and cosine. I don't think it's that difficult. So this is 0, pi over 2, which is 90 degrees, pi, 180 degrees, 3 pi over 2 is 270 degrees, and then 2 pi is 360. This would be negative pi over 2, or negative 90. This would be negative pi, which is negative 180. This is negative 3 pi over 2, which is negative 270, and negative 2 pi, which is negative 360. Now, sine of 0, let's do sine first, do it in blue. Sine of 0 is 0. And this is going to be negative 1, 0, 1. Okay, sine of 90, or pi over 2, is 1. Sine of 180, or pi, is 0. Sine of 270 is negative 1. This is also sine 3 pi over 2. And then sine of 2 pi takes us back to 0. So sine, sketch of sine looks like that. I'm not putting all the angles in, but it's going to have that type of curvature. Then you go backwards, negative rotation. Sine of negative pi over 2 is negative 1. Sine of negative pi is 0. Sine of negative 3 pi over 2 is 1. And sine of negative 2 pi is 0 again. So sine has this shape. Okay, and then same thing for cosine. Cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi, or 180 degrees, is negative 1. Cosine of 3 pi over 2, or 270 degrees, is going to be 0. And cosine of 2 pi, we're back to 1. And then you could go backwards. Cosine of negative pi over 2 is 0. Cosine of negative pi is negative 1. Cosine of negative 3 pi over 2, or negative 270 degrees, is 0. And then cosine of negative 2 pi, or negative 360, is 1. So cosine looks like this. And notice that sine and cosine are offset by 90 degrees, or pi over 2 radians. And we're going to use that information here to derive these next two properties. So show that cosine pi over 2 minus theta equals sine pi. So we just sketched it, so I'm going to do it again. So this is 0, pi over 2, pi, three pi over 2, 2 pi. I don't need to go all the way back to negative 2 pi here. I'm just going to go back to negative pi over 2. So sine, this is negative 1, 0, 1. That's the range of sine and cosine. So sine of 0 is 0. Sine of pi over 2 is 1. Sine of pi is 0. Sine of 3 pi over 2 is negative 1. And then 2 pi is this. That's one period of the sine function, and it would come back like this, okay? Then cosine of 0 is 1. Again, this is because of the unit circle, the coordinates on the unit circle. This is 1, 0, 0, 1, negative 1, 0, 0, negative 1. So cosine of 0 is 1. Cosine of pi over 2 is 0. Cosine of pi is, that should say negative 1. Okay, cosine of 3 pi over 2 is 0. And cosine of 2 pi is 1. So from this sketch, and cosine comes back like this. So notice that cosine of, so this isn't exactly what I'm doing yet, but notice that the cosine of theta minus pi over 2, that's going to be a shift of cosine pi over 2 units to the right. Remember what I talked about horizontal translations? It's kind of it's the opposite of what you think it might be. So this is a shift pi over 2 right. Well, here's cosine. If I shift cosine pi over 2 right, that puts me right here. That's sine. So that's equal to sine theta. But remember, cosine is odd. Is even. So cosine of theta equals cosine of negative theta. Therefore, here I can say the cosine of theta minus pi over 2 equals the cosine of the negative of theta minus pi over 2. Okay, and that is going to equal sine theta. Okay, so I'm going to take it from here. So this is the cosine of negative of pi over 2 minus theta, which equals sine theta, which is what we're trying to prove, which is what we're trying to show here. So we have this now. We're going to need that in a moment. So let's now go to sine of theta minus sine of pi over 2 minus theta equals cosine theta. So again, let's draw a quick sketch of sine and cosine. That's 0, pi over 2, pi, 3 pi over 2, 2 pi, and I'll just go back to negative pi over 2. Okay, so remember on the unit circle again, you've got coordinates 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay, so sine goes like this. Sine of 0 is 0, sine of pi over 2 is 1, etc. And kind of once you get going, you kind of know the pattern. Then you could go back to here, sine of negative pi over 2 would be negative 1. So then cosine at 0 is 1. Then it goes to 0 like this. Alright, so let's label the colors here. So sine is going to be blue, cosine is red. So like in the previous example, I'm going to start with the sine of theta minus pi over 2. Okay, so I'm shifting the angle theta, pi over 2 to the right, so I'm going, because minus pi over 2, minus is going to be a shift to the right, so I'm taking, here's sine, so I'm shifting it pi over 2 to the right. So right now I don't see anything that matches that. However, notice that if I take the cosine, which is red, and I flip it upside down, I get this. So cosine, or negative cosine theta is going to be green. So now notice, let's do this again. So if I shift sine pi over 2 to the right, it matches here, negative cosine of theta. So I can make that result right here. Okay, now, so we got that, but we want pi over 2 minus theta for sine. So now remember that sine is odd. So therefore sine theta equals negative sine of negative theta, because it's an odd function. We discussed that earlier. So now I can write that sine of theta minus pi over 2, remember it does equal negative cosine theta, but then this, well, we know then this, because of this, is equal to the negative of sine of the negative of the quantity theta minus pi over 2. Okay, which equals negative sine, flip well, this is the negative pi over 2, which is pi over 2 minus theta. Okay, so now we have that negative cosine theta equals this, so negative sine pi over 2 minus theta equals negative cosine theta, and if I divide both sides by negative 1, I get my result I want. Sine of pi over 2 minus theta equals cosine theta. Okay, so now we're ready to do our final proof. Okay, so let's write down the stuff that we just figured out. So we have that sine pi over 2 minus theta equals cosine theta. We have the cosine of pi over 2 minus theta equals sine theta. Then we have the cosine, and we'll say a minus b is equal to cosine a cosine b plus sine of a sine of b. Okay, so now let's start with the sine of a plus b. So using this property, I can rewrite this as the cosine of pi over 2 minus the quantity a plus b. Okay, then I can regroup this as the cosine of pi over 2 minus a minus b. b. Right, I'm gonna rewrite this because I don't want to get too much confusion on what letter is what. This notice could be written as cosine of u minus v equals cosine of u cosine of v plus sine of u sine of v. Okay, so I'm going to call this u and this v. So now I can take this is the difference of this and this, so I'm going to write the cosine of u minus v is going to equal, and again, this is the difference, this is u, this is v, so this is going to be, from this property right here, this is going to be the cosine of pi over 2 minus a times the cosine of b plus the sine of a, well, that's sine of u here, which is going to be pi over 2 minus a times sine of b. Okay, well, from here we go again. So cosine of pi over 2 minus a has to equal sine of a. Then we have cosine b plus the sine of pi over 2 minus a, we're now using this property, is equal to cosine of a sine b. Okay, so cosine of u minus v, though, from right here is equal to sine of a plus b. Which gives us our final result for what we were trying to accomplish in this video. So to make it look like what I have up here, I'm just going to reverse these. So I'm going to say sine of a plus b is equal to sine a cosine b plus sine b cosine a. Now it matches what I have up here. And this concludes this demonstration of why this property is what it is. If you found this video informative and you liked it, please give it a thumbs up and consider subscribing to my YouTube channel, The Math Dog. You may share the content of this video with others. Thank you and have a good day.